Digital electronic signals and switches. This is also slides, but we're going to look at basically different terminology we're going to use as far as digital signals go. And we're going to be dealing with the logic in here. We're going to talk about several logics. We're going to deal with something called TTL. And we're going to deal with another type of logic called CMOS. So what we're going to look at basically start off with transistor logic, or TTL is a lot better to say that. Transistor logic basically deals with, it runs off a 5-volt power supply. So it's DC. Transistor, it's just a repeat. TTL, transistor. Sorry. So it's kind of like stuttering.
Why do you need it?
We'll see why. The first one is what the digital signal comes into, and the second one is what we take the digital signal from. So the output on the TTL with input on a transistor, and then with output on transistor. That's why it's called TTL. So we got RTL, which would be resistor transistor logic, with input on a resistors and with output on transistors. We got DTL, which is diode transistor logic. Those are obsolete. We don't run into those. That was the way they came up through logic functions. First it was diodes, and then then they came out with transistors. We've been doing first of all, logic was done with relays, and we'll let y'all see a little bit about relay logic, and then it moved over to solid state. But what we're going to start off with first is so in TTL, 0 would be equal to a binary 0, and then 5 volts would be equal to a binary 1. Now, of course, it's not going to be exactly 0, and it's not going to be exactly 5 volts. And what we'll learn is the actual range that these could fall into. The TTL runs off 5 volt supplies. But it's actually, we'll look at this, and then the 5 volt supply might not be perfect. So they give you a leeway even on the power supply. TTL is usually 5 volts plus or minus 5%, which means you could legally run it on a power supply between 4.75 and 5.25 volts, and it would still be okay. If you get it above that, then your ones and zeros are not guaranteed. And we'll look at this on an oscilloscope. And we'll look at time, and we're going to start off with what we call clock waveforms of something that happens repetitive. So like this. So this would be a repetitive waveform. So when they start talking about most digital devices, not all digital devices, things have to be timed just to make sure everything's in the right place at the right time. So when we start talking about processors, we say it's a 1.2 gigahertz or something like that. And that's the actual clock that's timing everything inside the processor. Somehow all my icons got shifted around, guys. So we call this what? So from this, we call this the rising edge. we call this over here, I'm sorry, got that backwards. I'm thinking about the other one. Because this is going down, so we don't call this the rising edge. We call it the falling edge. And we call this the rising edge.
Why would it be the falling edge on?
Huh?
Because when it starts off at.
That's just where we're starting. We could start with the rising edge. We could start with the falling edge. That's just this signal. I started mine looking at the rising edge because that's what I triggered my scope on. And it depends on what happens. So we have different devices that we synchronize. If we're going to synchronize, we're not going to synchronize with a level. We're going to synchronize with an edge because you notice the level could do what? It could vary. So we got some devices, and so we have one we call it edge negative triggered or positive trigger. And that, so the positive, if it was a positive trigger device, then we would reference to the rising edge. If it was a negative trigger device, we'd reference it from a negative edge, right? Everybody okay?
So the negative you don't reference a negative edge, not positive.
It all depends on what system you're working with. Whether it times on the negative edge or whether it times on the rising edge or the falling edge. We do have some devices. Most of your computers now, to get double speed, it actually times on both edges. So, so you get twice the speed with a slower clock. Does that make sense? We call one repetition, and most people, if you had AC, you know this, we call one repetition, this is called a cycle. So technically a cycle would be one repetition of a repetitive waveform. No, it's somebody wrote the stuff upstairs. Y'all know we got it upstairs. The frequency is the rate of the cycles. In cycles per second. We ain't got to the period yet. This would be frequency. By the way, cycles per second, we could abbreviate that CPS, but we usually don't do that. Most of the people that are fundamental in the development of a technology gets the privilege of having their name given to different things. So the guy last name is Hertz, and he has the privilege of his name standing for cycles per second. So usually we would say Hertz, like Alabama Power sends out a repetitive waveform. Anybody know the frequency of Alabama Power? 60 Hertz. We abbreviate Hertz, uppercase H, lowercase z. Now, period is the time for one cycle. Now, time and frequency are inversely proportional, which means if frequency doubles, time will halve, which makes sense, right? Because if your frequency doubles, if I go from 60 cycles per second to 120 cycles per second, it means my Hertz is twice as fast. If it's twice as fast, then the time has got to be halving, right? You understand? So this guy would be like 16.666666 milliseconds. Then this guy here is going to be 8.3333. It's a repetitive number of milliseconds. Don't believe me, do you? I did that in my head. But what we do, guys, we can go, since they're the opposite of each other, we can always go to the opposite or the inverse by doing what we say, take the reciprocal of it. And what's the reciprocal? 1 over x. And we do this so much that every scientific calculator has a reciprocal key on it. It's either going to be labeled 1 to x, or it's going to be the x to the minus 1. Right? Taking a number to the minus 1 power is taking the reciprocal of it. So if you took 1, right, and took the reciprocal of 1, it's going to be 1. But if you took 2 and took the reciprocal 2, it's going to be 0.5, right? Because it's 1/2.
So K is the reciprocal frequency.
That's exactly right. Or vice versa. So I can, if I know the frequency, I can calculate if I know the period, it's going to be 1 over time. So we don't put P down there, we usually put time. Or the period or the time would be equal to 1 over frequency. Either one. So your scope measures time. Right? You understand? So it's measuring the period. So that 100 microseconds, and we had what, 4 of them? I think we had 6. So it'd be 600 microseconds. If I wanted to know the frequency, then I would just hit that and you hit the reciprocal key on my calculator, and that would give you the frequency. We should be close to 1,700 hertz. Is it 600 microseconds? Let me go back and remeasure. I think I played around with that. Let me look. So here's here to here. So that's 100 microseconds. 1, 2, 3, 4, 5, 6. 6. So it should have been around what? 1.7 kilohertz or something like that. Maybe that. Actually, it's 1.686. So an oscilloscope measures time. It measures voltage and measures time. Now, this is a computer. This is a digital oscilloscope. So I could tell it to give me the frequency, and it would do it for me. But you got to understand, I can buy an analog scope for $250. This guy, I can buy an analog scope for $250. This guy right here costs about $500. It'll do the math for you. So, of course, the digital, one of the advantage of a digital scope is it's a lot smaller, but it costs a lot more money. So I don't want y'all to use that feature. I'm not even going to tell you how to turn it on. Because if you can measure time with this oscilloscope, right, then you can measure it with any oscilloscope out there. Oops. Got my voltage up. And there's your formula. Repetitive waveform, specific time interval, successive pulses, or again, frequency period. Here's the formula right here. Are we okay? Any questions? Some of y'all said AC. So this should be. AC is generated on a repetitive waveform too. So this is a look. So what the duty cycle is? The duty cycle is the what? What's the duty cycle? The percent of the period that a digital signal is high. Well, that's another two terms we're going to use. So we're going to use high and low. High has nothing to do, and digital has nothing to do with those, right? So what we do is we come over here when it's at its maximum value. We say that the signal is high. And then when it's at its minimum value, we say the signal is what? Low. So this waveform here, you can actually see the duty cycle real easy. So here it's high, 1, 2, 3, and it's low, 1, 2, 3. So this guy would have a 50% duty cycle. Yeah, so when your high and your low is exactly the same amount of time, then the signal would be a 50% duty cycle. So what you would do to calculate the duty cycle is it's the percent of the period, right? So what's the period? What's the percent of the period? So here I would say 3 divided by 6, and that's going to give me what? 0.5, which is what? 50%. Everybody okay? So I'm going to change my colors. Green don't show up real well. So let's do red. And we could go either way, so I could start off here, right? So what would be the duty cycle here? Huh? 1, 2, 3. That would be 1, 2, 1, 2, 3. We have a total of 5. So that's going to be 3 over 5. It's the percent of the period that it's high. So this would be that it's high. So it don't make any difference what you start off with. It's the percent of the period that the signal is high. So this would be a 63% duty cycle. So what would the dead duty cycle? Yeah, so we got total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Over here we got 1, 2, 3, 4, right? So it's going to be 4 tenths, right? Which would be what? Huh? 40%. It's the percent of the period that is high. It has no difference what you start with and what you end with. First of all, we figure out the time for a cycle. Yeah. Right? Y'all understand that? So no matter what you start with, it's percent of the period that is high. The period is the time it takes for one cycle. The first thing I have to do is I have to identify a cycle. So this is my oscilloscope. So a cycle is one repetition. I can't see this leading edge over here real good, but I can definitely see this one over here. So I'd say, right? So we got it over 1 minor division. So my time is 1, 2, 3, 4, 5, 6. I don't care about the microseconds on oscilloscope. I could say 600 microseconds, but when I do duty cycle, I just count the number of divisions that's high and number of divisions low. So it's 5.1 high out of 6, right? So 5.1 divided by 6. That would be our duty cycle. It's over 1 minor division. Can you see that? Zooms in. Yeah, see, here's the edge, There's one minor division. If there's five between, if each one of these are ones, I'm sorry guys. If I'm counting these as ones, what would each minor division be? There's five of them. Huh? So it's actually 5.2. So what we got is, I'll do it up here, is I've got a division. Then I'm taking that division and I'm dividing it into 1, 2, 3, 4, 5 minor divisions. I'm saying this is equal to a 1. If that's equal to a 1, how would I get a 1? I can't say 0.1, 0.2, 0.3, 0.4. Oh, I got to end up with a 1. I got to end up with 1. So that means that's got to be equal to a 0.2. 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 And that would be a 0.2. So it means if it comes over right there, then that's going to be a 0.2, right? You understand that? So what you got to do, first of all, is look and see what you're counting in. If I'm counting in ones, then each minor division is going to be worth a what? A 0.2. What's nice about duty cycle is we're not concerned with the speed. We're concerned with the percent of the period that the waveform is high.
So right there on that oscilloscope, you have 1 at a high, and you have 5 at a low. So that'll be 1 out of 6.
1 out of 6.
Okay.
So we count the time for the cycle. 1, 2, 3, 4, 5, 6. It's 1.2 out of 6. 1.2 out of 6, right? Did I say that right while ago? Yeah, 1.2 out of 6 because this guy is over what? 1 minor division. So what would that duty cycle be? Oh, let me put my calculator back on scientific, right? 1.2 divided by 6. Here's my divide. Oh, so that'd be a 20% duty cycle. By the way, to calculate the average DC voltage, it's your maximum voltage times the duty cycle. So that means if I measure this, I got 5 volts, I got a duty cycle of 20%. What would my DC measurement be? So I'd say 5 times what? 0.2, and that should show me what my meter means. What the DC equivalent of this is. So my voltage is 5 volts. I got a duty cycle of 20%. So what would be the average DC voltage? So we got a 20% duty cycle. What's my maximum voltage? 5 volts, right? Okay, so take 5 volts and multiply it by 0.2. Huh? Y'all did get 20%, right? Not divide, multiply. My meter's not reading right. That's all I'm going to do. So our duty cycle must be off just a hair. This is what I measured. So if I had this signal hooked up to a DC motor, it would run like it's getting 1.1 volt. That's the speed it would run at. So what we do, this is one of the methods we use now because this is digital. It's off or on, right? And it's called pulse width modulation. And this is a technique they use now to run DC motors. So that means if I get a 50% duty cycle, this guy should, or I can measure this. Keeps covered up. I'm trying to move these boots back because we're not dealing with real high voltage. So this thing will keep pushing itself off. So that means when I adjust this up to 2.5 volts, it should be a 50% duty cycle, right? It's hard to see because it's not. Yeah. So what's really neat about this is the preferred method, and we'll talk about later on about power and stuff like that, control DC motors and pulse width motors. That's called the duty cycle. So what is the duty cycle?
So the period that is hot.
That a digital waveform is high. Everybody okay with these? Where'd y'all learn these at? DC. Usually in DC, you don't get down into Pico. You'll deal in these when you get into AC. Capacitors, when we get into capacitors. Capacitors are down here. Of course, resistors are where? Up in here, right? And the capacitors are down in there, and inductors are also down in the middle. Capacitors, you got pico and micro, and we call this engineer notation. Is it the same as in binary? No. So this is base 10, and it's what y'all learned back in DC, right? Engineer notation. This is base 2. So in base 2, binary, a kilo is 2 to the 10, mega is 2 to the 20, a gig is 2 to the 30, a tera is 2 to the 40. Pico, which we're not there yet. So right now we're in here. And we're not here on memory yet. In memory, we're still where? Still up here in the giga. And our mass storage device, like hard disk drives, we're up in the terabytes now. So in binary, they run in powers of 2s. So a kilo in binary is 2 to the 10th, which in decimal that would be equal to 1024. And then a meg would be 1024K, and then a gig would be 1024 meg, right? You understand? So in binary, we run in groups of 1024, which is what a K is. So here's another method. 2 to the second, 1024 to the third, to the fourth, to the fifth, to the seventh. This is actually what it does. Now notice every time it starts with 2 to the 10th, and then we don't double it, we just increase it by a power of 10 every time. And this is in binary, which gets very confusing. So if I looked at, I think this guy's got 8, how much? I think this guy's got 8 gigabytes worth of memory in it. But if I looked at the memory, it's actually going to be more than 8 gigabytes because they're giving it to me in binary, right? You understand that? Mass storage devices are usually given in binary. So y'all understand that? I know we're fixing to click. One more thing. Serial representation. We send data. You send information 2 different ways. You send it in. Now, what information? What the information flows through is what we call media. Media. That's a D. media. Y'all heard of me, multimedia. Multimedia means I give it to you in more than one form. So the media that we send data through is we usually send it through fiber optic cables. We send it through the air, right? Or we send it through electrical conductor. Sometimes the fastest method is parallel, which means every bit you send has its own conductor. And then, of course, usually 2 conductors per bit because you got to have a return, right? So that means in the old days on the parallel ATA drive, I would have 32 wires in the cable because it was a 16-bit interface, but for every signal wire we had to have a what? We had to have a return. So sometimes we don't have to do that. Some guys, so the advantage of the analogy I use for parallel is like the interstate system. You know, we got 2-lane roads, right, you understand, and we got 6-lane roads. Which one can we send more cars up? I can send 1 million cars on a 2-lane road, but it would take a real long time. Or I can send it on 8 lanes, right? You understand that? And we can send it more faster. So parallel is always faster than serial, but it's more expensive because it takes more media. So sometimes we have no option for the media. Like if I'm going to send information through air, then it's got to be serial because we only got one air, right? You understand that, right? So everything that flies through the air is serial communication, which means everything. I'm not going to tell you what we used to say in the Navy. That's back when I'm not going to tell you. I was in the Navy. The term "cuss like a slater," that's true. I was, of course, I don't do that anymore. But we were coming back from. My parents came down and picked us up for boot camp, brought my wife and my kid back. We was coming back and we stayed at a hotel, and we got back into our room, and my wife says, "I can't believe you said that in front of your daddy." And I didn't even know I was out. So in the Navy, you get where you use profanity and you don't even realize you're using it. So, but you got to understand the advantage of serial is that it's going to be a lot cheaper. And then sometimes we have no option but using serial. Right? Sometimes we use it because it's cheaper. Like Wi-Fi, what's it? Parallel serial. Serial. Yeah, Ethernet. Even wired Ethernet is serial. Serial ATA, which is our main method of USB. Universal. What does that stand for? Serial bus. It's serial. And we'll talk a little bit about those two. COM ports, which are basically obsolete. Serial ATA. USB, FireWire, which didn't get called on. FireWire and USB competed for a long time. FireWire, you still run into it. It's really, really good for video. High definition, high speed media. USB is the one that got adopted. Serial ATA. We're moving over, by the way, a lot of serial ATA because it's a lot cheaper, you know. But it's fast, but it wouldn't be as fast as parallel. What we have to understand when we send information, somebody's got to receive it. And it doesn't make sense for me to send information at 1 billion bits per second if it can only be received at 100, right? You understand? So like a hard disk drive or USB or stuff like that, it's stupid to use parallel because the device that receives it is not fast, right? You understand? Hard drives, they're fast, but they're still serial ATA does it clean is really, really fast. But the parallel drives don't need parallel anymore because why? Because serial ATA could run at speed to support all those things. So we're going a lot of things are going to serial now because it's what? Cheaper. Especially when I do hardwiring. And like I said, sometimes we got no option, right? You understand that? All right, guys.